I'm David Gray, engineer at Macalloy. I've been in and around Macalloy since 1990. Seem to have seen most things come and go, and a lot of that time I've been involved in the post-engineering and ground engineering side of the company. You might be interested in this. This slide is actually Ravenscar in North Yorkshire, and this is why they tell you not to sit underneath the rocks. Somebody actually managed to get that photograph just as it was collapsing. So we will discuss what soil nails are, where's the best place to use them, and the benefits of using stainless steel, and a little bit about selecting the most appropriate grade of stainless for a particular application. What are Macalloy bars used for? Well, they can be used as rock bolts, soil nails, or ground anchors. As a rock bolt, you're trying to achieve a stable column of ground which will hold back the rock face. For a soil nail, you're looking to install an S650 soil nail to increase the slip plane radius, therefore preventing the slip occurring. And on the ground anchor, you're looking to prevent the slip plane from rotating by holding it back against some competent ground. Soil nails and rock bolts are fully bonded. Ground anchors are partially bonded. For those of you who've not seen the Macalloy S650 anchor, this is one of the 316 anchors with a 10mm rock bolt plate and the standard 2.5 degree spherical nut attachment. Macalloy offer the full range of S650 bars from 16mm to 50mm, and that's giving us a range capacity in kilonewtons of 140 kilonewtons to 1487 kilonewtons. To prevent the slip from rotating, the nail penetrates the passive zone, increasing the length of the slip and hence increasing the force required to obtain movement. For a slip plane to work, it generally requires water to lubricate the transition phase. This is an area which has fresh oxygenated running water and so an area of high corrosion. This is also the area of maximum bending and shear, so a corroded bar at this point is highly stressed. Stainless steel will not corrode in such situations and so is not susceptible to the increased stresses. It is the area of high bending and shear, so a DCP soil nail may also have damage to the corrosion protection at this critical point. By civil engineering standards, soil nails are relatively new. Their first documented use was in Versailles in France in 1972, and their use in the UK has steadily increased from 2% in 1993 to just over a third in 2015. The early designs paid little attention to the aspect of corrosion. This is Dawlish seawall just along from the point of the major storm damage of 2014. This portion was damaged by an earlier landslide. The location of the landslide is clear from the lack of vegetation. There are many hundreds of stainless steel soil nails installed above the railway. The top row has rope anchors fixed to the plates for the rope access operatives to fasten to safely. The white flags you can see are telltales to give a graphic warning of any movement of the ground. If they lean over, a slip is imminent. Inclinometers are installed to remotely warn the rail company of any impending slips. Think about most cities around the world. We've built on all the suitable land, so now we have to build on the unsuitable land. Floodplains often require mini piles to accommodate excessive settlement, or cliff tops requiring rock bolts, as in this photograph of Hong Kong, halfway up the peak. In this durability section, we'll consider the types of corrosion and designing for its prevention. Considering the types of corrosion control, firstly, coatings. Galvanized is okay and painting, but of course they mess with the threads. You've got fairly tight tolerances on the threads, clearances on the threads, and when you coat them, you'll have problems. And of course, if you brush the threads on a galvanized bar, you will not have the same corrosion protection that you would from a fully dipped bar. Now on GRP, modern GRP is good in corrosion. However, the shear capacity can be very low, and it's expensive to achieve the tension capacity anything like that of an S650. So extra tendons or larger tendons are required to accommodate this. Sacrificial corrosion. To accommodate the loss of section during sacrificial corrosion, larger bars and hence larger boreholes have to be drilled. Extra anchors may also be required to compensate for the effect of corrosion with consequential extra costs. And just how confident are you with the corrosion rates you've adopted? And over time, things can change. Routes of roads can change, so the amount of salt going onto your anchors, and many different things can change. So over time, it's better to have a known anchor performance. Of course, stainless steel has good ductility, it's got a known corrosion performance, it's got very good shear capacity, simple to install, robust when installed, and it's simple to design. Just design the anchors and just put the stainless steel anchors in the locations where the corrosion is going to be an issue. So why do we need stainless steel S650 bars? One would be the freeze-thaw attack on the rock. Fresh oxygenated water will cause corrosion on a standard steel bar. The slip plane encourages fresh oxygenated water past the anchor, causing corrosion at the most critical and stressed area of the soil nail. The anchor head will also experience corrosion from rainwater and saltwater runoff. We should consider the whole life costing of the project, including maintenance and the more subjective costs, such as carbon footprint, extra inspections, those kind of issues. So what's the weight of a 4 meter by 25 millimeter rock bolt? Probably 15, 16 kilo. Say about 100 pounds each. A similar steel anchor is probably about 40 pounds. Seems a big cost difference. But the cost of installation in difficult locations is the critical issue, and it far outweighs the extra cost of the anchor. For a different presentation, I prepared a report on the cost of a roadside delay of only 10 minutes for a 2-lane motorway over 4 hours a day for 2 weeks of roadworks. The cost to the community was about €350,000, and the cost to the road user is about €150,000. So if only one maintenance mobilisation can be avoided, the S650 will actually save money. Over the life of the structure, stainless steel S650 will save money. Other considerations, such as carbon footprint, which is reduced. You've got reduced inspections, reduced maintenance, and smaller boreholes because you don't have to worry about sacrificial corrosion. All those contribute to the overall saving. So just thinking a little bit more about the whole life costing. So regardless of the whole life costing, for most applications, the cost of using stainless steel soil nails is actually more economic than carbon steel anchors. The extra cost required to accommodate sacrificial corrosion actually cost more than the stainless steel soil nails in the most popular sizes. And the benefits of stainless steel comes for free. This is the same information presented in a slightly different way. The break-even point for stainless steel is just under 20 years. The rope access crew estimates are from a major rope access company with agreed rates for rail work. The costs are based on extra anchors to compensate for sacrificial corrosion. Balancing the cost of stainless steel and carbon steel soil nails. Obviously, the initial cost of stainless steel soil nails is higher than that of carbon steel option. You need extra carbon steel bars to allow for the sacrificial corrosion, with the extra cost for both bars, drilling and labour. Later in the project, extra inspections and maintenance will be needed. Disruption costs to the client can be significant and easily outweigh the initial purchase price of stainless. Of course, the effective life of the structure is reduced when using carbon bars. Selective substitution with stainless bars is the most economic long-term solution. A common application for soil nails and anchors include the construction of new steeper slopes. This image shows us creating a large car park at the rear of a new shopping centre. Notice the use of geotextile structural grid, the white, to retain the slope, and the green soft facing, which would later promote stabilising plant growth. This is an old image of Macalloy soil nails on a retaining wall. Notice these stainless steel anchors are using a geotextile mesh to maintain the fines in place and also promote a natural vegetation to reinforce the embankment. There's a bungalow at the top of this retaining wall, and you can see the slip which is occurring at the top left-hand corner. Where it's difficult to maintain and repair a structure, long-life anchors need to be adopted. Stainless steel provides an economic solution for construction when compared against the cost of a mid-life repair, or the disruption to the client and their neighbours. Where the consequence of failure is dramatic, long-life nails should be adopted. Stainless steel performs well with careful selection of the correct grade, and a long-life, safe, economic slope design can be provided. Where geotechnical uncertainties are likely to be an issue, stainless steel has a bright future. It has been used in many varied applications as far back as 1927 in the foundations and of the refurbishment of St. Paul's Cathedral in London. The great thing about stainless S650 bar is its versatility. It can be a soil nail, a rock bolt, a ground anchor, and the applications are immense. A typical railway embankment stabilisation. When tunnelling and with roof bolts, the aim is to create an arch of reinforced ground to support the main body of the mountain above. When the East Coast Main Line was being electrified in the early 2000s, many of the tunnels were upgraded, requiring the floor of the tunnel to be lowered to give headroom for the pantograph cables. Stainless rock bolts were installed to hold up the Victorian brick-lined tunnels, and then a stainless mesh was fastened to the anchors, and the tunnel was then concrete sprayed. Anchors were also placed vertically down in some locations to prevent heave of the floor. Mini-piling and underpinning are standard rectification for bridges and buildings. However, the simplicity of the stainless nail or pile makes installation and assured longevity certain. The London Road Bridge in Doncaster is underpinned using exactly this system, using Macalloy bars. The use of stainless steel S650 holding down bolts or mini piles in onerous locations prevents the worry about the structure security. This image could just as easily be a wind turbine or a trackside pantograph column. S650 is a perfect tool to recover brick arch bridges, providing a high corrosive resistance in a harsh environment, and also having exemplary bond characteristics. This is achieved by post-tensioning the arch. Naturally, the loads are quite low, but the methodology is well understood. This is a typical rail-over-road bridge parapet. BSEN 1992 requires that any bar protruding through the surface of the concrete should be stainless steel, and the 316 grade S650 bar is ideal in this application. It should be fully threaded for the bond. Metric studding has poor bond. Threaded rebar is expensive and on very, very long lead times. And remember, Macalloy provide full technical backup. The secret to a good seismic design is to let all the individual elements move independently during a seismic event and then return to their original position. Here the pile cap is isolated from the bridge structure. During a seismic event, the pile cap will move, and not all that movement will be transmitted through to the bridge deck. In this situation, it's impossible to protect the bar and the anchor head from corrosion as it passes through the pile cap. So a 316 or duplex stainless is used in this location. Stainless steel is adopted because of its superior corrosion properties and relatively high ductility. So, in conclusion, what are soil nails? They're a cheap solution to soil instability. Benefits of stainless steel soil nails: easy to design and install. Design the structure once and later go through and select where the high corrosion resistance bars are required. Durability: fix and forget. Stainless steel's S650. Applications: road, rail, tunneling, underpinning, seismic, wind turbines. Thank you for your attention, and I trust that it has provided you with some ideas for the use of stainless steel anchors in the future.